we have Dr. Logan Liu from Electrical and Computer Engineering. And his talk title is Translational Research on Micro and Nanobionics Devices for Mobile and Social Sensing Applications.
Yes, so thank you very much for the invitation, and it's my pleasure to give this talk. And my talk will be slightly different from Chris's and Kathy's talk. And I'll talk a little more on application side rather than spending time on the detailed technology, because I only have 20 minutes here. So before I start my talking about my slides, I want to do a very short poll. I want to know how many of you own a smartphone here in this room? Almost everyone. Okay. How many of you own a computer with the optic drive? Now or before? Not many, of course, but people do use that sometimes. So the idea we have is really trying to not creating any new instrumentation, but just trying to create micro nano devices that can use them on your own computer, your own smartphone, okay, for mobile health applications. So you can diagnose your health in your home or on flights, on your cruise, or anywhere in the world. Basically, as long as you have a computer, you have a cell phone, you can do that. So here's, of course, this is still the so-called conceptual drawing. We didn't get to that point yet, but I think in 3 to 5 years, we'll get to that point that you will really detect your, you can do a blood analysis on your computer, you can do a blood analysis on cell phones. Okay, here's which one is laser? Is that red one? Okay. All right. So here I want to just maybe spend time on that. We want to make a micro nano sensor that can be coupled with the computer, so people can really just get a little bit their blood or urine or whatever biofluids onto that device, and that computer can help that sensor to detect the cellular and the biomolecule markers in that biofluids. And also the same idea is here if you have a cell phone, especially smartphone. The smartphone basically is a very, very small computer again. And we're hoping that we can attach a sensor to the smartphone so you can detect, for example, in this case, you can detect your cholesterol level in your blood. So you don't have to really go to your hospital to draw 10 milliliters of blood from your arms. Right? So that's our dream and our goal. So toward that goal, basically, in my lab, we're developing this micro nano sensor technology. Particularly, I call it digital health diagnostic lab-on-chip technology. What we want to do is we'll replace the hospital laboratory, of course, maybe not 100%, but at least to a very large extent. And we want to digitize medical information, because once you use computer and smartphone, the information tech is already inherently digitized. So that's very good for transmitting those informations through internet or wireless network. And of course, we want to connect our sensors, our smartphone and computer to internet and wireless network to get information sent out from your home to hospitals or to anywhere else. And of course, this is the most important thing. The reason why we don't want to make any new instrumentations, because we want to make this technology ubiquitously accessible to large population eventually. Because I cannot imagine any of you in this audience want to buy an optical focal microscope in your home. Nobody want to do that, right? You will not buy let's say, a fluorescitometer in your home. But everyone here has a computer, has a smartphone. So let's just use that as instrumentations, but with very, very good micro nano sensor to do that work. All right, so particularly today I'm going to talk about 2 examples in my lab. One is for biofluid analysis on a CD device. Another one is a drinking and recreational water analysis on a smartphone. Okay. So the first part is the picture is not coming. Okay, right here. So the first part of my talk today is microfluidic health diagnostic compact disc, what we call that as HDCD. It's not for high definition CD, it's a health diagnostic CD. So in the hospital, I think everyone in this room had experience like this. You draw a little bit of blood from hospital laboratory, and laboratory basically using very bulky, expensive, fancy equipment to detect your cell biomolecule markers in your blood for diagnosing disease, right? And so this is a microscopic pictures of your blood. Basically, you have red blood cells, white blood cells, platelet, and all kinds of invisible proteins in your blood. So why don't we just make some micro nano sensors that enable us to detect those cellular and biomolecular informations? So our strategy basically, what we want to do is we want to have a sensor that enables us to do the following things. That whatever you can detect in Hopsel lab for the blood analysis, we want to do that on our CD platforms. So here is, of course, just a few examples. By counting the blood, basically you can correlate that with some diseases like anemia, correlate with the red blood cell count. You can also do glucose metering. You can do that at home as well nowadays. You can diagnose diabetes or monitor your blood sugar levels. And by detecting cholesterol, then you can basically predict your heart functions. So there's many examples really beyond this table. But today I'm going to just show you some of our preliminary results. How do we do this on a device like this? Okay, I call this mind healing device, transforming to a health diagnostic device. Because before, 10 years ago, we used this to make ourselves more comfortable in our life, basically. But today, what we're going to do is transforming this by combining with microfluidics and nanophotonics technology. Well, believe it or not, there's already nanophotonics technology in the CD. That's been there for 20, 30 years. You have to make those sub-micron nanostructures to actually record binary information, the actual 0 and 1 on that CD. So by combining microfluidics and nanophotonics together on this platform, we want to use it in the computer. So as long as you own a laptop computer that has optic drive, we wanted to actually detect the cellular and molecular information on that CD platform. So the idea is very simple. If you have this diabetic lancet, or you have a micro needle integrate with that CD, basically you can just get very little amount of blood from your fingertip. And that blood, of course, will be introduced into microfluidics integrate on that CD platform. And then we use the optic drive on the computer as the instrumentation to detect the cells and biomolecules in your blood. So that's the actual idea. And the actual procedure is also very simple. For the actual patient to do that, they only need to press their fingertip on HDCD, extract a little bit of blood via microneedles, and that blood's getting into the microfluidics channels, and all you need to do is just place that HDCD in a computer optic drive, and everything else will be taken care of by the computer. Of course, we have to write our own software to analyze the information about the cells and the biomolecules. Okay, so, well, believe it or not, if you really disassemble your optic drive, you will find out this optic pickup really have very similar configuration as your confocal microscope. Okay, of course, one only cost $20, another one cost up to $500,000. Of course, in terms of performance, this one is much worse. However, for some application like only for cell counting or biomolecule detections, this is actually has enough capabilities. And especially nowadays, we have a better optical drives, especially for Blu-ray. You can get down to the resolution about 200 nanometers. So we're basically thinking about it, can we really use this optic drive as instrumentation to do confocal cell imaging on the CD platform? Okay. All right. So here's the basic configuration of our device. It's just start from a commercially available CD, but you have to do some engineering work on top. You have to thin down this polycarbonate layers. Well, this is layer is what you're talking about, nanophotonics layer, that you have those periodical nanostructures with different transparencies. So if you have a very opaque area, that would be recorded as a 0, and when you have a transition from opaque to transparent area, that will be recorded as 1. So that's how the bioinformation was recorded on the CD originally. But if you combine microfluidics on top of it and use the cells or label biomolecules on top of that layers, you're going to have some interference between these particles or molecule on the top with the actual nanophotonic bioinformation recorded on the bottom. And when you have a laser, optic drive start to read these formations. Okay, that beam will be either scattered or completely blocked by that cell particles or biomolecules, depending on the concentrations. So that's a basic technology idea we use to detect the actual cell numbers and cell shapes and the biomolecule concentrations. Okay, so eventually this is the problem that you basically have to convolute this biological information with digital information together on a CD platform. And what you read basically is the convoluting information from this tool. And our work has to basically to deconvolute this biological information from this convoluted data. Okay, so this is a kind of raw data we will acquire from this kind of CD platform that once you have sort of interference of your cells with the laser beam, you will see basically a peak right here. Okay? So by counting the peak and also by counting the intensity of the peak, you can correlate that with the cell numbers and then with the cell morphology. All right, so our first version of the device is made by soft lithography that we use PDMS as a material to make our microfluid channels and place that on top of a CD, of course, engineering CD. You cannot do this on a regular CD. You have to do some modification on the surface, and then you combine these two layers. So you now have these PDMS microfluid layers plus a digital CD underneath it. And on the microfluid layers, you can create all kinds of microfluid chambers and channels to introduce your cells and biomolecule solutions. All right, so this is our first version of a PDMS-based CD device that we have a PDMS layer made as a donut shape. So we have a channel like this allow us to introduce a microparticle and cells into that channels. All we need to do basically just, after introducing those samples, just place them onto OPI drive in the computers. And we wrote some softwares to help us to identify this information, to help us to basically deconvolute information from the raw data to the actual the cell number data. So here is an example showing we can do digitized cell counting on HDCDs. Once you inject these cells into microfluid channels, and that cell numbers will be reflected as the actual digital reading right here. And this peak intensity has very nice correlations with the actual cell concentrations in your samples. So we can do this in the microfluidics only by using a CD in your computer. So that's our first step to do to actually demonstrate that we can do cell counting. And then, of course, in your blood cells, you have red blood cell, white blood cell, and platelet. They have different size and shape. So now we're trying to combine those separation microfluidic structures on the CD platform to really separate the cell. I believe many of you actually use centrifuge in your lab to separate different biomolecules or cells depending on their size and their surface properties. Here we use very similar ideas, but not using a centrifuge in your lab, but using that spindle motor in your OPI drive to use that force to separate a cell, to separate large cell from smaller cell. Here we are basically creating multiple steps with different heights on that microfluid channels. So once you spin this CD, a larger cell will be capped on a large dam, and smaller cells will be just go through and be collected at different locations of your channels. And then after that, because they're separated out, so now we can not only do a cell counting for whole blood samples, we can also do a counting of individual cell types depending on their size, because you already separate them out on the actual CD. And also this kind of structure help us to immobilize the cells on a certain locations of your HDCD device, because once you're spinning the actual CD, once you're reading your CD, the actual CD is kept spinning. So you have to basically immobilize the cell once you do that. So this structure provides a very nice design to not only separate cells but also immobilize cells while you're reading the CD. And of course, after demonstrating we can do cell analysis, we also want to do biomolecule analysis, because that's how we can basically know the cholesterol, cholesterol level or glucose level in your blood. So we have demonstrated that we can do glucose metering on the same platform just by using a very conventional colorimetric-based glucose sensing assay and incorporate that on top of HDCD device. So we can, just by looking at the actual color difference through this, I believe this glucose oxidase assay, and by actually looking at the actual reaction activities, we can look at the actual color change. And by detecting the actual data related to the color change, we can correlate this actual information with the concentration of the glucose on the same platform. So eventually we want to integrate everything together in a platform so we can do not only cell analysis but also biomolecule analysis. So this is just an example showing you we can do that. So this is second generation CD we're making by doing collaboration with Singapore A-Star, because they have very good plastic-based manufacturing facility over there. So now the actual second generation device is completely based on plastics. There's no PDMS here. Everything here is made in plastic, just like your regular CDs. But on that part, we actually using is a microscale plastic injection and molding technology, plus this laser welding technology together, so you can create a microfluid layer made of plastics. And here's a showing that we can make just a single channel here. But eventually, we're going to have a very complicated microfluidic network to help us to separate cells and to concentrate our biomolecules. All right, so another task we're trying to conquer in our recent months is we're trying to do a more precise cell image rather than counting the cell, because as I said, because this optical derived technology is getting better and better, the actual resolution we're having now is really even below 200 nanometer. So what we want to do is, can we really do this? Can we really do the cell imaging on this HDCD platform so that we don't really need an optical microscope? We can just use this platform to do that. But of course, this is also a very big information theory challenge, because you have to do a lot of the convolution, a lot of the encoding and decoding to get information out. So after talking about that, and the second part of my talk basically is a mobile phone-based water nanosensor network. So what we want to do for this one is we want to develop a microscale and nanoscale electrochemical sensor can be attached to cell phones, allows us to actually detect the drinking water quality. Okay. Believe it or not, even U.S. Estimately, there's about 15% of people still get their water from private ground water source. So they're not really subject to the EPA regulation. There could be some potential dangers for the actual toxins or those contaminants get in the water. And in the whole world, every 20 seconds, a child died because of a water-related disease. And every year, more than 3 million people die because of water-related diseases. So what we want to do is really have this cell phone-based water sensors to allow everyone in this room, also everyone in the whole world, to have the ability to detect water contamination by using their cell phones. So there's also local problem here is because here we have a lot of fertilizer applied in our farms. So if this fertilizer is over-applied, potentially there's some risk that you could have very high nitrate concentration level in your drinking water. That could create some problem like blue baby syndromes. And also every year, because of these agricultural activities in Midwest, you will see this so-called hypoxia phenomenon happens in Gulf of Mexico, because we have a lot of fertilizer flowing down to the Gulf of Mexico through the Mississippi rivers. So what we want to do is basically have the ability to allow regular citizens to detect these nitrate concentrations or other water contaminants by themselves. And also to couple that with wireless network so that they can report information on internet and through the actual social media. So our solution is really the combination of MNTL and NCSA. This is the reason why we had one meeting yesterday at NCSA and today here at MNTL. So this is really nice combination, and I have to work with my colleagues in NCSA. We have to combine the nanotechnology, microtechnology with information technology together, and to combine our nano sensor plus circuit plus phone with phone app software and with cloud computing, and eventually with the social media. So everything is combined together, you can get information out. So we have done this, we have demonstrated the first prototype that we can do this water sensing on cell phone-based systems, and we have a circuit built, we have, of course, a sensor shown here, and to integrate with the actual circuit, and then the actual circuit has a communication function with the cell phone. And then, of course, this is not, this is only one part. Eventually, you can get information out from the cell phone to the cloud, and then through the cloud can start to broadcast information on the internet. So if one person doing water sensing in Urbana-Champaign, everybody else in Urbana-Champaign can know that water sensing result on internet. Okay. All right, I'll just quickly finish it. And so what we made basically is by using micro nanofabrication technology, we make this micro electrochemical ionic sensors. This is just 3 electrodes, sensing arrays allow us to detect the reduction peaks of nitrate concentration in the actual water samples. But what we also made is a portable circuit allows us to replace those bulky electrochemical instrumentations so that we can integrate everything into a portable systems. And this is a nitrate sensing result by using that portable systems, and we can do a very nice correlation of our so-called CV analysis to measure actual reduction current peak and correlate that peak intensity with the concentration of nitrate in our samples. And our current sensitivity is about 60 ppb for the nitrate sensings. So this is a picture showing that we really do this sensing and having the data showing on our cell phones. And then this data, of course, can be sent to the actual cloud, and we'll show you something like that. And of course, we have made our own software on our cell phones that allow us to control the actual sensor and to drive the sensor to get information applied on the cell phone, and also send information to Twitter, and then eventually get information out from the Twitter to your cell phone back again. Okay, this is showing that once you do the sensing on your cell phones, you will see this information come up on the actual Twitter site, and that, with information about contamination types, contamination concentration, geolocations, and time, and of course you can also send some words and a photo together with it. So eventually, this is basically what you can see on the public website. When somebody using this portable sensor to do water sensing, they can really see the information about what they actually sense. Here's a showing example that we can actually sense the nitrate concentration in one location of the Urbana-Champaign areas. At the same time, you get also information from other existing sensor networks like USGS sensors and also EBI weather stations in South Farm. So of course, eventually you can also get information back on your cell phones. So everything really becomes very integrated systems that you have a sensor, cell phone, and cloud, and social network. So as a summary, we have demonstrated that we can do microfluidic-based analysis on this HDCD platform in a portable computer. We can also do water ionic sensing on mobile phone micro nano electrochemical sensors. And this is really a combination of a micro nanotechnology with health IT technology. So as acknowledgement, I want to thank my student Manas, Xinghao, Jimmy, Tewei, especially for doing this mobile phone water sensor work, and Syed, Hassan, and Galson for doing the CD work. And my faculty collaborators, Jiping Wang in Singapore A-Star, and Barbara Minsker in Civil and Environmental Engineering Department, and Yong Liu in NCSA. And the funding from Summit, Monsanto, Searle, and NCSA, and NSF Kaplan Center. Thank you.
can you talk about sample preparations for the CD experiment? Are you using whole blood or are you processing blood for the CD?
That's a very good question. So for the blood analysis, for the real blood analysis, the clogging is a problem because you have, we have, once you have a blood out of the bodies, that will become solid in just a few minutes. So we have to basically use those anticoagulation agent together in the blood. So on the actual introduction, I'll go back to this. On the actual inlet of our channels, let me show you a second version of device. So in the inlet here, of course, when we do experiment, we can just manually mixing those anticoagulation agents with the blood samples. But in the future application, we will want to do just blood injection. We have to store some anticoagulation agent preview. Just store that in powder in the actual microfluidics. So once you have a blood sample flow in, they can mix together with a pre-stored agent, so that blood can stay as a liquid for a very long time until all the detection has been finished. So that's one of the main concerns when we do blood analysis. So far when we do the real biology samples, we really have to mix them with those anticoagulation agents before we inject the sample into the microfluidics. Okay. All right. Thank you.